In most cases found in the literature today, formation controllers consists of two main loops, as seen in this block diagram, the inner loop and the outer loop. The inner loop aims to achieve local stabilization for a single agent in the formation, while the second loop, which is the outer loop, is tasked with achieving the desired formation by coupling the agent's states through a common formation control law. So, in other words, the inner loop is responsible for the control for each agent in the formation, because when I want to control a formation of agents, each agent should be controlled and should be stable. So this is the responsibility of the inner loop. Usually we use, like, for example, PID, controller, flatness-based controls, backstepping, etc. However, the formation level controller is available in the outer loop, where the formation controller is used there. So the outer loop feeds its output as a generated reference points for the inner loop. So if you want to give a general idea, the formation controllers consist of two loops, the inner one, which is responsible for the control for each agent in the formation, and the outer loop, which is responsible for the formation global controller, in other words, to control all the agents together, while the inner loop control each agent alone. Okay, this is the formation controller concept. However, when we talk about formation control, we focus on the outer loop, because the inner loop and the control of each agent is a lot of works consider such a problem, and there are a lot of controllers used for such cases. So we usually, when we consider formation control, we consider the global controller of the formation. In other words, the outer loop. Formation control structures. Formation control structures that are used in the literature today are leader-follower structure, virtual structure, and behavioral-based structure. We will start first by leader-follower structure. In this structure, one agent is designed as a leader, while others are treated as followers. If we look, for example, on this figure, this bird, we usually see the birds flying in such shape. The birds, this is the leader, and these are the followers that follow the leader. So the formation flight mission trajectory, or the formation mission trajectory, in case we are using ground robots, not flying robots, is loaded in the leader. The mission trajectory is loaded in the leader, only in the leader, which is very interesting, while the followers are tasked to track it in order to achieve and maintain the formation. Leader-follower structure, of course, has advantages and disadvantages. It is desirable and attractive due to its simplicity and its wide implementation in multi-agent formation, where it is enough to specify the leader's motion in order to control the whole group. Moreover, the leader-follower configuration is considered as an energy-saving mechanism, in addition to its simplicity in the stability analysis, which is very important. On the other hand, if we want to consider its disadvantages, the main disadvantage of such system is that the entire formation depends on one agent, which is the leader. So if there is a problem with the leader, the whole formation will be affected, and thus making this approach poorly robust to the leader's failure. Also, error propagation and non-self-organization are disadvantages of this control structure, where there is no formation feedback for the leader from the follower, which could lead to a problem if one of the followers couldn't catch up with the leader, especially as I mentioned that there is no feedback from the followers to the leader. Okay, so this is the leader-follower structure that is used, it's widely used nowadays. The second structure that exists in the literature today is the virtual structure. In such a structure, the formation is treated as a single geometric entity. In other words, a single virtual leader is used to coordinate the motion and the behavior of the agents in the formation. Thus, trajectories are calculated in a central computer and shared with all the agents in the formation without any interactions between them. Then, each agent in the formation has its own trajectory to follow, where the group of all trajectories form the desired formation. So, in other words, we have a virtual leader. It could be like, for example, a central computer. In such computer, we calculate all the trajectories that should be followed by each agent, and these trajectories are shared for each agent in the formation. When each agent in the formation follow its trajectory, the trajectory of the whole formation and the formation is going to be achieved. Note that there is no interaction between the agents in virtual structure, as far as we know. Let's consider its advantages and disadvantages. This structure solves the problem of reliability and error propagation presented in the leader-follower structure, since each agent follows its own trajectory independently of any other agent found in the formation. Not like in leader-follower, where we are depending on the leader. We are only depending on the trajectory that we are following. Also, virtual structure formations are desirable since it is enough to specify a trajectory for the virtual leader in order to prescribe one for the whole formation. However, such structure is undesirable due to the rigidness of the formation. This limits the range of applications that can utilize such formation. Moreover, since there is no interaction between agents in the formation, collisions could not be avoided in such system. Finally, one of the main drawbacks of virtual leader structure is the increase of the computational and communication cost during the formation control, which accordingly reveals a problem in scalability. So when we increase the number of agents in the formation, we are going to increase the number of computation, especially in the virtual leader. Okay, so this is the virtual structure. Finally, which is really interesting, is the behavioral-based structure. In this structure, the formation control task is broken down into smaller tasks referred to as behaviors. So the formation task is broken into smaller tasks, okay? These behaviors are then weighted based on priority levels and thus averaged in order to generate the formation control actions. If we want to consider that such sentence is complicated, in other words, each individual in the formation will follow a set of rules, so the overall behavior is the combination of the several sub-behaviors. So we have a set of rules. Each agent in the formation is going to follow this set of rules, and when every agent in the formation follows this set of rules, the formation is going to be achieved. So each agent converges to a global objective of the formation in order to accomplish the desired formation. Of course, it has some advantages and disadvantages, but before we consider them, I want to highlight that such a structure depends on the motion of animals. Like as seen in these figures, This is method that is inspired from the motion of fish, from the fish school. So look how they are moving. So some systems considered such motion and controlled the formation of UAVs inspired from these motions. So this is an example of fish school, whereas there is another examples of bee schools, where we are inspired from the motion of bees. Usually such works depends on the use of objective function, maximization or minimization, etc. Now let's consider the advantages. One of the main advantages is that a behavioral-based structure is easily self-organized, since each agent has to follow a set of rules and knows the objective, trajectory, or destination. Also, one of the most important advantages in such a structure is the scalability, which can be seen when increasing or decreasing the number of agents in the formation. As seen in this figure, since it is inspired from the fish school, we have the advantage of increasing the number of agents in the formation. Especially that in such a structure, usually each agent is going to interact only with its neighbors. So it is not necessary to interact with all its neighbors, which will increase the computational time. On the other hand, if we want to consider the disadvantages of such a structure, is its unpredictability that can occur in averaging the weighted behaviors. Also, one of the main disadvantages is that we can't ensure a fixed geometrical pattern of the formation, since it is hard to guarantee that the formation has converged to the desired configuration. In other words, patterns such as V-shape, as we have seen, like the birds are moving, the V-shape, the rectangles could not be formed. So this is a very important problem in such a structure, in addition to the stability analysis, which is really, really hard in such structure. Formation control classes.